Thank you, Bertand, for the introduction. Yeah, that's true. It's been a year now. Okay, first of all, I just want to say hello to everyone. And okay, so today, as Bertand said, I will present the work that I've done in the last year together with Quentin, Jean-Paul, Kévin, Juhel, who's recently joined the group here at Josur, and Bertand Rouet-Leduc, who's in Los Alamos. So the work will mostly focus on the analysis of the prompt elasto-gravity signal, or shortly PEGs, using deep learning aimed at estimating magnitude and also its potential for operational early warning systems. So this is a brief outline. I will go a little bit to give you an introduction about PEGs. Then I'll show you what our deep learning model looks like. And then I will talk about two different things. First, we're going to focus on estimating the final magnitude and location from PEG signal. So assuming that, that an earthquake has happened. And in the second part, we're going to perform a timeliness analysis on the magnitude estimation and put the work more in a context of operational early warning system. And with future work and conclusion, I will finish my presentation. Okay, let's start with PEGs. So first of all, what is the prompt elasto-gravity signal, or shortly PEGs? PEGs is a signal that is generated by the gravity perturbations induced by the displacement of a large amount of mass during large earthquakes. These gravity perturbations propagate at the speed of light. So this means that PEGs arrives at a given location before the fastest seismic waves, so the P waves. The existence of PEGs was predicted by theory, but the very first observation of the signal is quite recent and is due to Montagnier et al. In 2016 for the Tohoku-Oki earthquake. That happened almost 10 years ago. It will be an anniversary soon. So to show you what the signal looked like, here I just show the observed and modeled PEGs waveform with stations sorted as a function of distance from Tohoku source. The x-axis here is time relative to the Tohoku origin time, and the waveforms are cut at the P wave arrival time. So we're looking at a portion of the seismogram before the arrival of P waves. So what we can see here is that there is a long wavelength and coherent signal along these stations, and this is very interesting because we can first notice one thing, and it's that PEG's maximum amplitude depends on magnitude. So here, this can be seen, for example, from the observed in red and modeled amplitude for Tohoku, which is 9.1, compared to the maximum amplitude reached by PEGs for a simulated 8.5 earthquake. So this means that, yes, PEG's amplitude depends on magnitude that can be useful in the context of magnitude estimation. So a second observation is that amplitudes are very small. This is the scale; it's 1 nanometer per second square, and which is reached for Tohoku, but they're even smaller for a magnitude 8.5. So this means that likely it's going to be very difficult because of the low signal to noise ratio to detect this kind of signal. Another observation is that amplitudes of PEGs, max amplitude of PEGs, they have they show regional patterns. So this means that to extract as much information as possible about the source, we're going to need to work with an array of stations. Okay, in this quite complicated slide, I would like to give you a better idea of the observational settings for PEGs and where this signal comes from. So what does a seismometer really measure? So when a large earthquake occurs, the displacement of mass and the mass redistribution generates gravity perturbations that propagate at the speed of light in all the medium. So in turn, these gravity perturbations act as body forces, here indicated by red stars, that induce some elastic waves that arrives at the station here before the direct wave generated at the earthquake location. So all these signals are plotted here for 2 stations and related to Toku. This is the green line is the direct gravitation, the gravity variations, while the blue line is its induced acceleration, and the black line is the simulated pegs, which is the difference between the two. So it's just the gravity variation minus the induced acceleration. So as you can see, the good news is that we're able to model with simulation the observed signal in red. The bad news is that for pegs, which is a combination of elasto and gravity waves, and that's why it's called pegs, at the early part, there is a cancellation effect that reduces the potential detectability of pegs. Here they show very low magnitude, even though the gravity variation are bigger, especially in this part. So in principle, we would like to measure the green curve, but this is very difficult because we don't have instruments with enough sensitivity to do that. But it's very important. In the next slide, I will show you how. So, and I will call the red, the green curve, so the direct gravity variation at PGS, so prompt gravity signal. So Juhel et al. Showed through simulation what we can achieve by measuring and using the prompt gravity signal, so the direct gravity variations in the context of early warning. So they did a simulation in which they show if we could measure this signal, we would be able to have an amazing performance in the context of early warning. Here they show that they can robustly constrain the moment released by the Tohoku earthquake, starting at about 15 seconds, and even something a bit before. And so this could be transformative for an earthquake early warning system. So I want to stress again that these are simulation, and instruments with enough sensitivity to measure this kind of signal do not exist yet, but they are under development, and these gravity strain meters will be very useful in this context. But at the moment, we don't have this kind of tools, so we need to do with what we have, which is our beloved pegs. This is exactly what we have, and this figure shows the pegs detectability, and basically shows all the pegs observation made so far on large earthquakes occurred in the last 30 years. As you can see, only 6 observations were possible due to the low signal-to-noise ratio. And the current detection limit is 7.9 for a strike-slip event in Alaska. And it's been possible through the stacking of a lot of stations from a very dense network. These figures also show the dependence of PEG's amplitude on the type of focal mechanism and depth. So, for example, if we take a strike-slip event here, this magnitude 8.6, Wharton Basin, or a deep slip event, as in Bolivia, we can see, which is an 8.2, we can see that the amplitude of pegs, it's similar to what we see on a larger earthquake, but from a shallow deep slip event, such as Tohoku. So what this means is that shallow deep slip events, which have the highest tsunamigenic potential, and these are the ones that we're most interested in, are not likely to be observed for magnitude lower than this, unless some sort of stacking is performed, as for example, for the Maule earthquake, in which stacking of different stations allowed to detect the presence of pegs. So, however, this kind of stacking makes application to real-time early warning system very difficult. So, exactly in the context of early warning system, this type of earthquakes that we're interested in, so shallow deep slip events, are the most critical, as they are associated with intense ground shaking and can produce destructive tsunamis. So the purpose of this work is just focusing on this type of earthquake and try to assess the potential for magnitude estimation and also timeliness using PEG's data. That's the objective. So that's what I said, assess PEG's potential for early magnitude estimation operational early warning systems. So in order to do so, as apparently we're dealing with a very faint and noisy signal, we try to rely on the ability of deep learning to perform this task. So a little introduction about this. Deep learning has proven to be effective at discovering hidden relationships in the data or to extract information from a coherent signal buried in noise, which is exactly our case. This simple sketch illustrates the main advantage of deep learning with respect to conventional machine learning technique, which is basically to automatically extract information and relationship between the data without the need of ad hoc or specifically engineered feature. So as long as the training is performed on a huge database for which the ground truth is known, then we can learn a mapping from the input to the desired output. In this simple sketch, the algorithm, the model is trained to learn if an input image is a car or not, which is a classification problem. And in our case, this will be replaced by regression, and we will try to estimate magnitude and location. So this is more or less what we're gonna try to solve. So it's a very blurred and noisy image made of PEGs data, and we're gonna try to extract magnitude and location from this data using deep learning from the waveform recorded at a full seismic network. So this is not new, and it's an increasing area of research. Most of the, so this slide is pretty busy on purpose because I wanted to show you that more and more people are using deep learning for this specific task to estimate magnitude and location from waveform and seismic data. The majority of the work so far I've used convolutional neural networks, but there are some exceptions, as the work done by Martin, Van Ende, and Ampuero, which they use a graph neural network to extract even more information from the dense array of stations. But in general, this convolutional neural network approach has proven to be effective, even if they worked on only one single station. And they show that the problem of earthquake location can be solved with one single station, which was something that we wouldn't have expected a few years back. So in our case, we're going to use the full information from the full seismic network to even better constrain our parameters, magnitude and location. Very few real data exist for PEGs for which the ground truth is known. And at the same time, deep learning requires a vast amount of data with this characteristic to be properly trained. So this is simply impossible with PEGs because we have, as I showed, 6 observations. So we need to rely on synthetic data. We mostly focus on the Japan subduction zone, and we use the 74 broadband station locations with good quality data that will be used for noise waveform. I'll show you later. So the database is made up of 500,000 synthetic earthquake sources, each of which location is chosen at random from a model of existing model of subduction geometry, SLAB 2.0. So once for each source location we select, we extract at random a value of the moment magnitude, uniform between 5.5 and 10, because we want our database to be as complete as possible, and that's why we want our model to perform good on all the range of magnitude. And we also extract rake from a normal distribution with mean 90 and standard deviation of So in order to compute synthetics, we need some synthetic waveforms. We need some source time function. And in this work, we use an empirical model based on Meyer et al. 2017. So the functional model for a source time function is it's here, and lambda is the parameter that control the characteristic duration given a value of the magnitude. We started by using like a fixed duration for different values of magnitude, but we use a multiplicative noise term to include the variability in the source time function in a way that we can also simulate bimodality or variation in the moment as a function of time. Once we extract a source time function for a given event, we can generate synthetic data, which are shown here in red for two station locations, which are this one and this one here, for a source of a magnitude 8.9, which is located where the red star is. So what we did to simulate more realistic waveforms was to add empirical noise to the synthetics. So this is actual noise recorded at the stations in the database. And we use a fixed time window of 350 seconds starting from the earthquake origin time. Here I just show like a cut version of it, but we use 350 seconds. And we bandpass filter the waveform between 2 and 30 millihertz. And then we sort traces by station longitude in a way that this is fixed during training and at a given test time. Then what we do is we set amplitudes to 0 after the P wave arrival, and this is to ensure that we have that we're only dealing with pegs data, so we don't have contamination from P waves because we want to assess the potential of pegs in magnitude estimation. At the same time, this implies that we assume that the P wave arrival is known, and this is not a big problem because we have triggering algorithms either based on deep learning or not that can provide this information on quasi real time. But this is what we do because we want to just be sure that we're using only the information containing the pre-P time window. Then we clip and scale the waveforms to kind of facilitate the convergence of learning. And at the same time, we're scaling by a constant factor not to lose the information of the radiation pattern and the relative amplitudes between stations. And then 5% of the station are randomly muted to simulate missing data. So then we compute this for 3 components. Here I just show one, but the input of the network is made of 3 of these images. And this is what the network look like. It's a very simple network based on convolutional layers with dropout, which is this blue layer here, which helps in to prevent overfitting of the training set. And so the input data are images like these, and the output are 3 real values that corresponds to magnitude, latitude, and longitude. The main part of the network is made of this convolutional layer, which extract the main feature of the input data, while 3 dense layers at the end perform high-level reasoning to map this feature into the final labels. So it's common practice to divide the database into training, validation, and test set. So this is I show what they look like, and they all have similar distribution, which is important in this case. But we basically use the 70% of the database for training, so to learn the mapping from input to output, 20% of the database to validate the model and tune the epoch parameter of the model. And the last 10% is used as a test set. So these are examples in the database that have never been seen by the model, so we can once we feed them into the final train model, we can assess the performance of the model itself. So labels are going to be magnitude, longitude, and latitude. This is the performance of the model during training. As you can see, training and validation set are very similar. It means that the model is able to generalize from the training to the validation set. This is a function of epoch. Each epoch means that the training has seen all the data in the training set. And as we progress with learning, the model learns better, as quantified by our loss function, which is the mean absolute error. Okay, so finally some results. As I said, we're gonna see first the results for estimating final magnitude allocation with this fixed time window approach. And later we move on to the timeliness analysis. So these are the results for location, which are pretty good. But here we have to keep in mind that we're using the p-wave arrival time as a constraint. So for the model, it's a bit easier to. It's a strong information, so it's a bit easier to recover that. I'm not going to talk about location anymore during this talk, and I will just focus on magnitude. So these are the true value and the predicted value. As you can see, there is a one-to-one relationship. So these are the distribution of the residuals, and the errors are from 15 to 20 kilometers on both. But I'm gonna focus more on magnitude because that's the most interesting parameter so far, which is totally inferred from PEG's data. So these are the results for magnitude. This is a density plot between true values, so the value of the labels, and the predicted value on the test set. So as you can see, we can identify like two clusters of solutions. So the first cluster starts at about 7.7, 7.8, goes up to the maximum value in our database. It's actually 10, but it's okay for display here. It shows a one-to-one relationship, which means that the model is able to predict the true value of magnitude pretty well in this range. While if we move below 7.8, let's say 8, the solutions tend to cluster here. This seems to suggest that below 7.8, these data do not contain information, the necessary information to estimate magnitude. So we can also look at this a bit more closely by looking at the evolution of the residuals as a function of magnitude. Here, these are box plots for which the red line is the median, and this is the interquartile range, and the whisker at 95. Contain 95% of the data. What we can see, so these box plots are colored by the probability of belonging to cluster 1. So it's actually 1 here. But so as you can see, while we go down in magnitude, this probability kind of decreases. So we can say that below 8, these data do not constrain magnitude pretty well. On the other hand, we can see that uncertainties on the prediction get smaller as a function of magnitude, which is actually pretty interesting because this means that we're able to distinguish, for example, a magnitude 8 from a magnitude 9, which for some point source algorithm employed in some early warning system, this is still a challenge, as we will see later. We can also play a little bit with the results and come up with maps like this. So ultimately, we're interested in to know what's the confidence level on when the true magnitude is not known, and if the algorithm predicts a certain value of the magnitude. So this map here shows you what's the probability when a predicted magnitude is predicted by the model that magnitude is above this value here. So for example, if the model predicts the magnitude 9, there is a more than 95% probability that the true that the true event has at least a magnitude, is at least a magnitude 8. So with this kind of sketch, we can use this to guide and facilitate the interpretation of the result. We can look at this more closely if we, for example, get horizontal slices over this map. And let's say we want to fix a value of probability for which we're willing to take action in the context of early warning systems. For example, let's say it's 90% probability. So this is telling you that if the model predicts a magnitude 9, there is a 90% probability that the earthquake is actually above 8.6. And so on. For example, for a magnitude 8, 90% is above 6.6. Okay, so once we tested on the test set, we also apply the model on real data. And we try to estimate magnitude for Tohoku. So what happens here is just we get the data, real data from Tohoku, and we feed this data into the model that is already trained, and we get some output values for magnitude and locations too. And we use Bayesian dropout to estimate some kind of uncertainties on this prediction. And as you can see, the predicted value agrees pretty well with the true value from the USGS catalog. And standard deviation is about 0.13, and the algorithm does a good job here. It also works pretty well with location, as I said before, and these are the posterior distribution for latitude and longitude, and the solution, the true value is within 1 sigma, so it did a good job. We also tried to apply and predict this value on a relatively smaller earthquake, so the 2003 Hokkaido earthquake. And what's important here to see is that, yes, so the mean value is actually pretty good. It's 7.9, and while the true value it's about 8.1 and 8.2. But what's important, okay, uncertainties gets bigger, and this posterior distribution looks a bit skewed. So this confirms basically what we observe on the test set, and that uncertainties will increase as magnitude decrease. And this is kind of reassuring, because it means that our test set, which is made of synthetic, is actually pretty good. Right. So, but ultimately, what we want is a model that is able to perform in almost real time and for operational early warning systems. So we try to adapt our model to perform this task, because so far we just seen we just use a fixed time window of 315 seconds starting at the origin time. And now we're going to try to assess what's the performance on the model as the magnitude, as the earthquake evolves, basically. So this is the current, this is basically what happens with P-wave based earthquake early warning systems. So these are known limitations of this approach for point source algorithm. So the first problem is for large earthquakes, when magnitude is estimated based on 3 or 4 seconds of P waves, magnitude estimation tend to saturate, and so under predicting the true value of the earthquake, which this is the source time function of Tohoku from Skardek, which is about 9, and this is a known issue that the GMA predictions for this event were underestimated because of this fact. And also, second fact is that even if we were able to correctly predict without this underestimation saturation problem for magnitude, we would still have like a shifted version of the source time function due to basically the speed at which the information is travels from the source to the receivers, which is the P waves in this case. So in principle, PEGs can fix these problems, because as we've shown, There's no magnitude saturation for earthquakes above 8, for example, because below that it's a bit more tricky to use pegs, but there's no magnitude saturation for large events. And in principle, the information contained about the source travel at the speed of light. So we should be able to track the moment released by an earthquake instantaneously. So in order to do that, we had to change the way we train the model. And this is a new learning strategy that we use. So we basically, this is the same as before. We start from the origin time, for example, and we take 350 seconds of data. And we assign a label in this case, which corresponds to an integrated source time function. In this case, is an 8.9 earthquake. So if we integrate the source time function, we get the moment released as a function of time. And we assign as to this data a label that corresponds to the value of the blue curve at the end of the time window. So in this case, it's just above 300 seconds, and we will assign something like 8.9. So the earthquake is basically finished. But what we do is that during training, we perturb this, we shift this window in a way that it can that we can use this type of just this portion of the data. So, for example, we start 200 seconds before the earthquake origin time, and we end here at about just a bit later than 100. What we do also is that we remove from the network all the stations for which we don't have P-wave triggering, and this is done to ease the learning, but this can be improved too. But so basically, as time progresses, what we do, and we assign to this window the value of the source time function at that time, which in this case is just above 8.5. So by doing this, so randomly perturbing the portion of the data that we are analyzing and changing the labels accordingly, we hope that we're able to track the release of moment as time evolves. So these are the results for being centered on magnitude 9 with a 0.1 width. What is shown here is the density plot of all the predictions made within these magnitude beams. And as a density plot, the red line is the mode of the distribution, and this is the interquartile. The dashed lines are the interquartile range, while the purple line are the true value of the labels with some uncertainties due to the noise in our source time function. So what I did was to mute and only make predictions with a constraint that 10 stations should be available. So at 10 stations, we should have P-wave triggering. And if we don't have that, we don't make any prediction. So after that, we start making prediction. And what we can see is that something at about 30 seconds, the mode of the distribution starts to align with the true value. And this is pretty well recovered all over the time. So in fact, what is happening is that the algorithm is able to predict the value of the moment released at that time instantaneously. So this is pretty, that's pretty interesting, because that would mean that we're able to get rid of the latency due to P-wave. We still have latency here, which is related to this number of station constraint. But as soon as PEG's data are assimilated by the algorithm, these are used to predict the value of the moment at that time. So to better visualize this kind of results, I built an accuracy map as a function of predicted magnitude and time. So here we define successful prediction as a prediction that has that is within plus minus 0.4 magnitude units between from the true value. and we just compute the number of successful prediction and the number of unsuccessful prediction, and we compute the accuracy. So this is a bit, this still has the 10 station constraint. That's why you have this delay here. And this map is a bit, it's obviously a bit smoothed because we need to, we smooth both on X and Y axis, but it gives you like a first idea of what are the capabilities of this model. So uncertain, and this is the map of the residuals. It's the mean residuals in each grid point. So this is basically telling you that for a magnitude 9, we're able to track the moment release pretty well, starting at about 30-40 seconds after origin time. Still okay for a magnitude 8.6. For a magnitude 8.2, we start to have some problems, and we get to we only start to have successful prediction, let's say with an accuracy of about 80%, just after 150 seconds. A magnitude 8 seems to be not useful in this case. However, I try to filter out based on the noise condition of the test set. And so if we only include data for which the standard deviation of the noise is below a given threshold, in this case is 0.5 nanometer per second square. So these are very low noise condition. What we can see is that in such low noise condition, even a magnitude 8 starts to be can be detected after a certain time, let's say 150 seconds. So this gives like a rough idea how to interpret our results. And but what's important here is just that we try to apply this on real data. So the next slide, you will see what are the results on Tohoku earthquake. So basically what we do is just we shift the data that we have in time, and at each time shift we make a prediction of the magnitude at that time. So these are the results. So the orange line is the integrated source time function from Bletery et al. 2014 that is calibrated against different types of observable. This light blue line is the JMA prediction, and the blue line is the mean prediction of our model. Using Bayesian dropout, we can also compute some uncertainties. And what this is, again, very similar to what we observed on the test set. So we still have this 10 station condition. So we don't make prediction up to 40 seconds. But after that, at about 55 seconds, information contained in the pegs, they give us an estimated magnitude that seems to match pretty well, actually, the integrated source time function. So this means that we're tracking as time passes the evolution of the magnitude. This is pretty good, because even if in principle we have this 40-second shift or system latency that we don't have data, as soon as we have it, we're able to track the magnitude instantaneously. We also tried the same with Hokkaido. And once again, these results confirm what we seen on the test set. So there's no chance that we're gonna see anything below 8. And in fact, until pegs amplitude are big enough to be detected, the algorithm just stays at this kind of operational level of about 7, or a bit more than that. But when some information comes from pegs around 150, even with higher uncertainties, but this seems to go on the final magnitude at this stage. So future work, there's a lot to do. And mostly we need to expand the variability in our source time function database. Training can be improved with different techniques in deep learning, as for example, LSTM modules that are specifically good for time series analysis. We can also design different learning strategies based on selective station criteria. So, for example, we can group and only keep active stations that have similar P-wave arrival time, and so this could improve again the estimate of magnitude as a function of time. But among all these things, I just wanted to show you one thing, which is waveform denoising. So this is a deep learning technique that aims at recover noise-free signal from very noisy input data. And so in this case, you have this seismogram, which is very noisy. And if you feed it into this type of neural network, which are called autoencoders, you're able to separate the signal from the noise itself. So this looks like something that we could be useful for our PEGs data, which are very noisy in general. And in fact, I did some tests, and we'll just show you the results of it quickly. So this is an autoencoder working on the same type of input data that we discussed at the beginning. So these are the input data, very noisy waveform. This is the ground truth, which is basically the input data without the noise, so the noise-free synthetics. And this is what the algorithm predicts when it's fed with noisy data. So in principle, it should it should be able to output the noise-free version of the data. So this is at epoch 1. At epoch 1, so starting training, it doesn't really know, can really distinguish, and you get a lot of blurred images. But as the training progresses, this is epoch 80, for example, you can feed the network with noisy data, and the output of the network is something that really resembles the noise-free synthetic data. So this could be critical for PEGs, as we've seen they usually have very low signal-to-noise ratio. But if we're able to map these noisy data into noise-free waveforms, we can probably improve the performance of our model even more. So I leave you with the conclusions. I show you that PEGs data has an applicability to earthquake with magnitude above 8, which is something that was kind of an assumed or an agreed minimum threshold for sensitivity in PEGs. But we show this for a deep sleep event, which in fact they have a lower signal-to-noise ratio than strike sleep or deep sleep events. So what I've shown you is that we were able in our timeliness analysis to perform instantaneous tracking of the moment release, which it's actually pretty impressive for just working with data that comes before P waves. So we're not using P waves at all. We're just using information from the portion of the seismogram before the arrival of P waves. Show you that prediction errors decrease with magnitude, which is particularly useful in the context of early warning, especially for large magnitude events. For Toku, we can make predictions that are about 15 seconds, which are basically tracking the evolution of the moment. Given this time scale and the fact that magnitude information is very important for tsunami early warning, this is probably the first application or most useful application of our model, so tsunami early warning systems, because we have predictions with in about like a minute, which could be very useful. The model and training, it's easy to scale to different focal mechanism and tectonic settings. We just have to retrain with a different database of earthquakes and stations. And finally, our model can be combined with additional observables, like using seismic waves to our GPS data to increase the performances. Thank you.